Hello, welcome to a new video. And this video is a continuation of the properties of isomorphism of groups. In a previous video, we have discussed many properties, some six properties we discussed. 5 or 6 properties we discussed in a previous video. In this video, we are going to see another property. See, the statement is for a fixed integer k and a fixed group element b. So B is a fixed group element for a fixed for a fixed integer k and a fixed group element b in G. The equation x raised to k equal to b has has the same number of solutions. See, it has some solution, then it has the same number of solutions in G as it does as does the equation x raised to k equal to 5b in G cap in the second group, which is the isomorphic image of the first group. See, we have the two groups G and G cap. The second group is the G cap, that is the group G cap. It is the isomorphic image of the first group. And then there will be the isomorphism phi from G to G cap. Okay. Then we consider, and also we consider equations of the form x raised to k equal to b. See, x is the unknown here. X is an unknown, so we can find the value of x. Those values of the value of x will be then selected from the first group. Here, when this equation is considered, we are selecting values from the first group. Those values or those members of the first group which satisfy the equation are the solutions. And you can count the number of solutions, and after that, you can consider a similar equation, but this equation belongs to the second group, that is the isomorphic image of the first group. That equation is x raised to k equal to 5b. So x raised to k equal to 5b. Here still x is the unknown. We want to find find an element or choose an element which fits this position. So x raised to k equal 5b. 5b is the image of the element b in the second group. But the property says that if there are 5 solutions to this equation, then there are 5 solutions to the second equation, and vice versa. How can we prove this? Consider the set S containing all distinct solutions of the equation x raised to k equal to b. See, we consider the set S. See, the set we define as set S, which contains all the distinct solutions of the equation x raised to k equal to b in G. Then we can write that assuming that there are R solutions, total number of distinct solutions are R, then S is equal to A1, A2, etc. to AR. We list the solutions, then S is equal to set A1, A2, etc. to AR. And then you know that we can substitute these solution values in the equation. We can substitute the values in the equation x raised to k equal to b, and then we get that a1 raised to k equal to b, a1 raised to k equal to b, a2 raised to k equal to b, and a3 raised to k equal to b, etc. ar raised to k equal to b, a1 raised to k, a2 raised to k, etc. equal to b, all are equal to b. So for each, this is true for all I equal to 1, 2, 3, etc. to r. And then in general we can write that ai raised to k equal to, thus in general we can write ai raised to k equal to b. Similarly, consider all the distinct solutions of x raised to k equal to 5b in G cap, that is S cap equal to that set, that's new set S cap is equal to set C1, C2, etc. to CT. Suppose it contains T elements. So S cap is equal to C1, C2, C3, etc. to CT are all the distinct elements of S cap. See, whenever AI is a solution of x raised to k equal to b, we are now going to show that whenever AI is a solution of the equation x raised to k equal to b, then the same element is the solution of then we know that AI raised to k equal to b. And then by applying phi on both sides, we get that phi of AI raised to k equal to phi b and that is phi of AI, and then applying a previous property, previously discussed property, one of the properties that we have discussed previously. We can get here phi of AI raised to k. So phi of AI raised to k equal to phi b. Thus phi of AI raised to k equal to phi b we get, and therefore phi a is a solution of, that means phi a is a solution of the equation x raised to k equal to phi b, x raised to k equal to phi b. uh, and therefore it is a, so whenever AI is a solution of of x, a raised to k equal to a raised to k equal to yeah, then x raised phi of a raised to okay, then um, yeah, that gives that AI, whenever AI is a solution, then a raised to k is a raised to k is a solution of the equation x raised to k equal to phi b. uh, then conveys also, we can prove conversely, we can prove the conveys part also. Conveysely we can prove that whenever ci is a solution of the second equation, see, whenever ci is a solution of the second equation, xi raised to k equal to phi b, and then we get that the corresponding there will be a corresponding member in the second in the first set. See, okay. And also since we are going to discuss that part, and also since AIs are distinct, see, all AIs are distinct, therefore 5 AIs are also distinct, all 5 AIs are also distinct. So so we know that we can say that the set 5A1 5A2 etc to 5AR, so the set corresponding image set of the set S, that's phi of S. So phi A1, phi A2, etc. to phi AR is a subset of S cap of the set S cap. Therefore, R is less than or equal to T. Thus, R is less than or equal to T equal to cardinality of S cap. When then that's the now we have to discuss the conveys part, and that is if Ci is a solution of the equation x raised to k equal to phi b, x raised to k equal to phi b in G cap, and since Ci is an element of G raised to n, since Ci is an element of G raised to n, their axis Y is an element of G. See, since Ci is an element of G raised to n, we know that their axis Y is an element of G, such that phi of Y equal to Ci. See, then and then phi of y the whole raised to k, then you can write that phi of y the whole raised to k equal to Ci raised to k equal to phi b. And therefore when we combine this, you can get that, you can rewrite, you can write the first part as phi of y raised to k. So phi of y raised to k, the first expression becomes phi of y raised to k equal to phi b, and therefore therefore since phi is 1 to 1, so now is applying the property that phi is 1 to 1, we can write that phi raised to k equal to b, phi raised to k equal to b in G, because already we have this phi b equal to yeah, since we have phi b equal to phi of phi raised to k, and using this and then property that phi is 1 to 1, we get that phi raised to k equal to b. And therefore y is a solution, whenever y is a solution of yeah, then this means that y is a solution of the equation x raised to k equal to b. Since y raised to k equal to b, y raised to k equal to b in G, and therefore y is a solution of the equation x raised to k equal to b. And thus this means that whenever there is a solution for the equation x raised to k equal to phi b, we get a corresponding solution for the equation x raised to k equal to b. And therefore we can say that cardinality of S is equal to T is less than or equal to R. So cardinality of so the number of elements in S cap, see, number of elements in S cap can be at the most the number of elements in S, that is cardinality of S cap is equal to T is less than or equal to R is less than cardinality of S, and this means that cardinality of S is equal to cardinality of S cap, and thus the proof is complete. Okay, thank you.